Very good. Well, hello, everybody. It is our great pleasure to welcome back to familiar face. So Dr. Tathagata Paul is here, graduated back in 24 spring. Yeah, he was, we did great work. So it was all on his shoulders. We made a couple of discoveries and all that. And then he got a postdoc at NASA Goddard. And that, so he'll talk about that. It's called the NPP. What else to say? Great to see you again.
Yeah, it's great to be back in the department. Yeah.
So without further ado, teach us about Roman space telescope, which is his new job.
Thank you so much, Dr. Wardy. Do I get a lapel, like a microphone or something?
Yeah. We hear you. Do you want one?
I don't think so. Like, if you guys can hear me, okay, cool. People online, can you hear me? I take that as the answer. Okay. All right. Thank you so much, everybody. Thank you so much for coming. So my name is Tathagata Pal, and I did my PhD from this department almost a year back now. And it's so great to be back to the department. And today I will be talking about one of the upcoming space missions for NASA. It's called the Nancy Grace Roman Space Telescope. And it's titled the next flagship mission for NASA. Like after Hubble, James Webb, we have the Nancy Grace Roman Space Telescope. And I'll also give you guys a brief overview of what I have been doing as like an NPP fellow, working with the Roman Space Telescope. So we'll start things off with giving you guys an overview of what Roman Space Telescope is, what are the different survey strategies, and what kind of science that we can do with the data that this telescope is that it's scheduled to collect. So potential launch date, nothing has yet been officially announced, but it's going to be sometime in September this year. So we are pretty close to the launch. It has a 5 years prime time mission duration that can be extended to 10 years. It will be at L2, and the primary mirror for this telescope is going to be around 2.4 meters in diameter. And that is comparable to the mirror for the Hubble Space Telescope. But the difference with Hubble is the field of view. So Roman is going to have 100 times the field of view of what Hubble currently has. So with one pointing of Roman, you could observe around 0.28 square degrees in the sky with just one pointing. And the key instruments that this telescope is going to have are called the wide field instrument, the WFI, and there is another thing called the coronagraph instrument, or the CGI. So the wide field instrument is the workhorse for the Roman Space Telescope. And the coronagraph instrument is it's going to be used for technological demonstration for future NASA missions like the Habitable World Observatory. So mostly we'll be focusing on the wide field instrument for this talk. And I'm also going to mention one point here about the Roman Space Telescope. So the Roman is a survey telescope. So there is no proprietary time limit for the data that it's going to collect. So 75% of the observation time has already been allotted to 4 different surveys with no proprietary data sheet. And 4 of them are called the High Latitude Wide Area Survey, High Latitude Time Domain Survey, the Galactic Bulge Time Domain Survey, and the Galactic Plane General Astrophysics Survey. I am going to talk a little bit in depth about each of these surveys in a while. So this figure here, it kind of shows a comparison between the Hubble, James Webb, and Roman. And you'd see that for Hubble and Roman, they have the same size of the mirror. But the big difference between Hubble and Webb with Roman is that the field of view. So you could see with just one pointing of the Roman observatory, you could cover like half of the Andromeda galaxy, and that too at Hubble resolution. So let's talk a little bit more about the instrument, the one that I was mostly talking about, the wide field instrument, or the WFI. So this figure over here, it shows the whole wide field instrument, and it's not just one thing, but there are different parts to it that's like put together, and it's a part of the telescope. Some of the parts of WFI are called the relative calibration system. So Roman WFI has its own calibration system. That's RCS. The EWA is the element wheel assembly. So that is going to have all the photometric and the spectroscopic filters. And the main part of WFI is the detector. So there are going to be 18 detectors at the focal plane. And that detector is going to provide a field of view of around 0.28 square degree on sky. And like these detectors, they are arranged in a 6x3 pattern. So like each individual detector is going to work on its own. But when you put everything together, you could have like a very holistic view of the sky with all of these detectors put together. Okay, let's talk a little bit about the Roman capabilities. So now we have the Roman Space Telescope, then you have the WFI, the wide field instrument. So, and then you have the element with the assembly that has all the filters. So Roman is going to have 8 different filters for imaging and 2 different filters for spectroscopy. So the imaging filters is going to cover like from visible, you could see that around from like one of the filters, the minimum starting wavelength is around 0.48 micron. And the highest it would go is around like 2.3 micron. So the band pass it covers is from the visible to the near IR. That's with the imaging. And for the spectroscopic, so for most part of my work that I am doing currently, I am mostly focusing on the spectroscopic aspect of Roman. So there are 2 spectroscopic elements. One is called the grism, and another one is called the prism. So the grism has much higher resolution compared to the prism, but slightly less coverage in terms of wavelength. So you see that for the grism, the wavelength coverage is from 1 micron to 1.93 micron. So that's in the near IR. So the good thing about like having a spectroscopic ability in near IR is that there are a lot of stellar population spectroscopic features that fall within the visible band that like when you go to higher redshift, it goes transferred to the near IR. So you could do stellar population analysis using Roman at a much higher redshift than what you could do with like the other observatories that are in the that operate in the visible band. So again, for this talk, I would mostly be focusing on the grism element, yeah, we'll see. So this figure here, it currently shows like the different filters, like how they are spread across the wavelength. And as I was mentioning, it starts from visible around 0.5 micron and goes till around 2.25 microns. And here is a curve for the grism right in between the bandpass. It's from 1 micron to 1.93 micron. So with the main, like the motivation behind creating Roman was that we needed to create something for the community that anyone in the community, anyone in the world could use freely. So with that in mind, all the surveys for Roman that I was talking about are actually created by taking inputs from the community. So that's why these are called core community surveys. And there is also another general astrophysics surveys. So 75% of Roman's time Roman's observation time is going to be involved, like doing these surveys. So the four surveys are the High Latitude Wide Area Survey, the High Latitude Time Domain Survey, the Galactic Bulge Time Domain Survey, and the Galactic Plane General Astrophysics Survey. So let's talk a little bit about like each of these surveys. So the first one is called High Latitude Wide Area Survey, and as the name suggests, it's going to observe on the higher galactic latitudes. So it has got 4 tiers. The first one is the wide tier, the second one is the medium tier, the deep tier, and the ultra deep tier. Now, out of these 4 tiers, only 2 tiers, the medium and the deep tier, they're going to have the spectroscopic ability. I know I'm always coming back to the spectroscopic ability because that's what I have been working on, but it would have like excellent imaging abilities as well over the wide, medium, deep, and the ultra deep tiers. So if you see for the, let's take for example the medium tier, it covers an area of around 2400 square degree on sky, and like that's over like 5 years. So that's a lot of data. So Roman is expected to create like petabytes of data every year, and like this is one of the surveys where we shall be able to observe galaxies. So none of the other surveys will have the capability to observe galaxies, specifically for spectroscopic analysis. But the High Latitude Wide Area Survey is going to observe at least, like the estimated number is around billion galaxies over its like 5 years of mission time. And if you look at the depth, the imaging depth and the spectroscopic depth, so the imaging depth is around 26 AV magnitude, which is which is pretty good, I'd say. Like it's going to it won't be able to observe sources with an AV magnitude of 26, and for spectroscopy, the flux limit is around 5 times 10 power minus 16 arcs per second per centimeter squared. So this is the survey that my work has been focused on, but it has a lot of other imaging capabilities as well on like away from the galactic bulge. So it doesn't get as crowded. The next one we have is the High Latitude Time Domain Survey. Now, the main motivation behind doing a time domain survey at the high latitude is we wanted to observe supernovae SN1A at for like these galaxies. So one of the major science goals for Roman is that we wanted to see like different kinds of clustering, and we also wanted to observe like the cosmic expansion using supernovae as a proxy. So this survey, the High Latitude Time Domain Survey, is going to do that for us. It has got 2 tiers, the wide and the deep tier. And like each of the wide and the deep tiers again have a north, and like it's divided into like 2 different regions, north and south. And you'd see that this survey does not have any prism capability. So it does have a spectroscopic element, but that is with the prism, which is of like much lower resolution. But probably it would be good, like it's sufficient for studying the supernovae, but maybe not for stellar population analysis, like galaxies and all. So there are like 2 different cadences, the 5 days cadence and 10 days cadence. So basically we will get like keep getting data every 5 days and every 10 days from the footprint. The next survey that Roman is going to do is called the Galactic Bulge Time Domain Survey. So it's going to be a very, very crowded field. It's primarily focused on the galactic bulge. But why do we want to focus Roman at such a crowded field? Like, what's the motivation behind doing this? So the motivation behind doing a galactic bulge survey is that we wanted to find out more exoplanets. So Roman is expected to find around 100,000 new exoplanets with transits. And for transits, you would need like very high cadence data, like photometric data. And you'd see like the highest cadence for this specific survey is 12.1 minutes. So Roman is going to get data from the galactic bulge part of our galaxy every 12 minutes. That's the highest cadence for Roman. And it also has got other low cadence seasons, but that's still like 5 days around. It also has 6 hours. But again, this one is mostly focused on getting photometric data. So because we want to find out different exoplanets that are there within our galaxy, so we are focusing mostly on photometric data for this specific survey. And the last one is the most recently defined Roman survey. It's called the Galactic Plane General Astrophysics Survey. So for this survey, we are going a little bit out from the galactic bulge, and we are focusing more like on the wider part of the galactic plane itself. This one again has like 3 different parts. The one in white, it would only have photometric time domain observations, and it's around 700 square degrees. And within this like white footprint, you could see like there are like this cyan blocks. These are going to be like, there are 6 of them. And this is going to be a time domain observation within those specific fields. So these fields were chosen after like specific inputs from the community, and people were interested in those specific regions. To be honest, I don't exactly know why, but if you move towards this, I don't know if you could see it, but these like small orange blocks here, like spread all across the plane, these are places where Roman will also do a spectroscopic survey within the galactic plane. Now, what are we trying to achieve with this spectroscopic survey within the galactic plane? So what we are trying to do is we are trying to create a library for stellar spectrum from a plethora of stars that we would see within this region. But the problem is grism that we are going to use for spectroscopy here, it's a slitless grism spectroscopy. So and it's a very crowded field, right? So there are going to be huge overlaps between like different spectra from within the region. So that's why Roman is going to observe these specific spectroscopic fields with 2 different orientations. So that way it helps us disentangle the spectra, the overlap spectra. So with all of these surveys and all of these instruments, what kind of science are we planning to do? So let me walk you through the science motivation behind creating Roman. So, but as I mentioned earlier, it's a survey telescope. The data would be available right after it gets observed. So you are free to do any kind of science that you want with the data. That's totally up to the community, what you guys want to do with that. But the motivation behind creating these surveys were threefold. The first, we wanted to have like a very wide area imaging and spectroscopic survey in IR. And the second is charting the cosmic expansion with measurements from very distant supernovae. And the third is also getting detecting different exoplanets within our own galaxy. These three were the main motivations behind creating these different surveys with Roman. But as my talk suggests, that you can do a lot of other things. You can do stellar population analysis. You could do whatever kind of science you want with the data that Roman would give you. But broadly speaking, these were the three science goals for Roman that people had in mind when they were building Roman. Oh, I forgot to mention one thing. Roman would also be able to detect a large number of weak lensing events. So weak lensing, if the source is not too bright, then the signal is extremely faint for weak lensing. But with Roman's capabilities, we should be, and extremely high cadence, we should be able to observe a large number of weak lensing events within the footprint of Roman. And that would actually help to detect more exoplanets, not just from transits, but also from these weak lensing events. Now, as I mentioned, it's a community-driven mission. So there are a lot of ways that all of you can get involved with Roman. So the first and foremost, the Roman Cycle 1 call for proposal is open. So I say 75% of the Roman's time is already dedicated towards these different surveys that I was talking about. But there are still 25% of the time remaining where you could submit your own proposal for observation. So by knowing what kind of capabilities Roman have, you could propose new observations which do not fall into any one of those categories. So the Cycle 1 call for proposal actually asks for call for those different observations that are currently not there in Roman surveys. But more importantly, within the Cycle 1 proposal, you could also submit proposals that would do some analysis with the already available data. So all the data are free. So it would be available as soon as they're observed. And then you could submit proposals saying that, hey, we are going to get this type of data from these different surveys, and I want to do this science using this specific data. So that is also another big aspect of the Roman Cycle 1 call for proposal. So if you are interested in submitting your proposal, the deadline is coming up on March 17th. So please scan the QR code. It will take you to a page where you'd see how to. It's pretty straightforward, submitting the proposal. The second one is the Roman Research Nexus, and this is very unique. I personally have not heard anything like a research nexus before, at least for Hubble or JWST. So what Roman Research Nexus is, it's a cloud-based computing platform. So as I was mentioning, they are going to be petabytes of data every year. So it might not be feasible for you to download all those data into your own computer and then running your whatever you want to do with that. So they have come up with something called the Roman Research Nexus, where you could create your own account and you would log in there, and it has a Jupyter Hub interface, and you could do whatever analysis that you want with the data directly within the Research Nexus. So you don't have to download any data. You don't have to download any software, any tool, nothing. You just have to have your account and then start working there itself. So if you are planning to submit a proposal for Roman, you would also be asked if you want any computing time, if you need any computing time within the Roman Research Nexus. So you could totally ask for it, and it's up and running. It's still at a very a nascent stage. There are a few problems that we are seeing every day, but I would highly recommend, if you are planning to submit a proposal, then ask for time within the Roman Research Nexus. So another thing is the Roman science collaboration. This is also very, very important because I say like only 25% of Roman's time is reserved for like new observations, right? So if you want to make an observation and you see that people around the world, they're also interested in very similar things that you want, then you guys can collaborate. So that way, like if there's a big collaboration and if you submit the proposal together, then there is a higher chance that your proposal might get selected compared to if you are just like submitting your proposal alone. So I'm not saying that it won't get accepted if you are submitting it alone. It totally might get accepted, but it just like increases the science outcome from Roman if you are like collaborating with other people who have like very similar science requirements as you are. So for that, we have the Roman science collaboration groups where people from different fields but with similar interests, they come together, they talk about writing up a new proposal and everything. And the last one is the Roman working group. So the Roman working group actually oversees the like all the different activities that Roman is doing before launch. So there is a simulation working group, there's a calibration working group, like all like if you have expertise in any one of these categories, there are a few other categories as well. I would highly suggest join one of those working groups. You don't need to make an account or anything. You could just send them an email and you could just join one of these working groups. So now let's dive a little bit into what I have been doing as an NPP fellow, like what my project is on using the Roman. So as I mentioned earlier, Roman is planned to observe like billions of galaxies at quite a large redshift range. Now, for stellar population analysis, you would need a spectra, right? You would need galaxy spectra. Now, Roman's high latitude wide area survey is the only place where you could get galaxy spectra. So my project is mostly focused on the high latitude wide area survey footprint and specifically the medium and the deep tier because only those two tiers have spectroscopic abilities using grism. And with with the data that we will have from these two tiers for this specific survey, we could do some kind of stellar like galaxy formation and evolution studies using different spectroscopic features. So for my work, I am mostly focusing on ETGs or the elliptical galaxies. So elliptical galaxies are those which do not have any ongoing star formation. So they are not really plagued by any emission lines unless there is a very strong like AGN or something similar. But my focus is on elliptical galaxies and then using a Roman grism, how can we do some kind of galaxy formation and evolution studies? So this figure here shows a flow chart that describes like what I am planning to do with the Roman data. So mind you, like I don't yet have any data for obvious reasons. So all I'm doing is like simulation work. So I start off by creating a mock galaxy spectrum. So for ETGs, there are a lot of SPS models that could create the galaxy, like a galaxy spectrum. If you give in like the metallicity, the within a specific redshift range, and then within those simulated spectrum, you look for different spectroscopic features that you can use for your galaxy evolution studies. So once you identify those spectral features and you have your mock ACD ready, then you create a catalog of the galaxies, but this time within the footprint of Roman. So within the footprint of the high latitude wide area survey, you create a catalog of mock galaxies. Like again, like these are not real galaxies. You just assume that we have these mock galaxies within this footprint. And then how Roman is going to observe those galaxies using the grism. Now, the main part for this flowchart for this objective is creating the grism simulation. So like whenever you are observing something, each and every instrument would add some kind of noise. Each and every instrument would have their own problems. So it's very important to know like what you are expected to observe. Like whatever you are planning to do, would you be able to do it with all the limitations of the instrument that you are using? So once you simulate the grism scene, then you can actually like start extracting the. So once we have the actual data, we would actually start from the fourth step here. So you would have the data, the grism scene data, and then you would start extracting spectrum from those the grisms. But for the simulation work, you have to do all of these previous steps. And once you have extracted the data, then you are going back to your SPS models. You are going to fit those data with different models and then see if you could recover the input data that you started off with. So when I wrote this proposal, I thought that I'm going to use some IMF sensitive data. So IMF is the initial mass function. So it gives you an idea of like when the galaxy formed, how many, like what was the ratio of like the giant versus dwarf stars. So it's a very, very crucial element for any kind of stellar population analysis. So I was thinking it would be good to see like different kinds of IMF sensitive features. Another reason was like these IMF sensitive features, these are within the optical band pass, but with Roman's IR capability for grism, you could actually look into higher redshift regime and see how the IMF has evolved at those higher redshifts. So that was the initial motivation of using, like trying to use the IMF sensitive features. So this figure over here, so this is a figure for like a mock spectrum for a galaxy using an SPS model, the worthy model, at native resolution for and the shaded region here, it shows a specific IMF sensitive feature. It's called the NAI doublet feature at a rest frame of 8,200. But at a redshift of 0.75, it got redshifted to within Roman's wavelength coverage. So this is how it looks like. This is how it is supposed to look like if you are looking at a spectrum at this redshift for this specific galaxy. But the thing is, this figure, it was at native resolution for the model. Now we had to make sure that Roman would be able to observe this. So we had to degrade the spectrum. We had to degrade the mock spectrum to match Roman's resolution and then see what is left. So as you can see here, like compared to the previous figure, there is absolutely nothing left. So for grism, the resolution is around 600 over the span of the wavelength. But when you degrade your mock spectrum to Roman resolution, you see that it's not observable. So and mind it, this is without adding any kind of noise or anything from the detector or anywhere. It's just like purely similar spectrum, but just degraded to Roman resolution. So even after degrading, we see that we don't have anything. We won't be able to observe any, like at least at this redshift, we won't be able to observe those specific IMF sensitive features. But the good thing is there are a lot of other features that you could use for different studies. So for example, this feature over here, the sodium D line, the NAD feature, it is pretty strong. And it's again, this is at a similar redshift at 0.75. And you see like the wavelength coverage is for Roman, So it is within Roman's grism wavelength coverage. And you see there are features like the sodium D line, the H alpha, the calcium lines. You could use that for figuring out the metallicities for the galaxies. So those still seem to be surviving even after degrading the spectra to Roman resolution. So we are kind of shifting our focus now from like those IMF sensitive features to these other features. Okay, so next. So for the simulation work, my main goal was to create the grism scene, right? Like how would Roman observe those galaxies and how it would disperse that along the dispersion axis for the Roman grism. So for the grism simulation, there are three main components. The first one is the ACD that I showed you. Like we have the mock spectra from galaxies for like different redshift at different metallicities and different age. The second thing that you would need is what is called a direct image. So a direct image is nothing but an image for the scene. Like whenever Roman is observing something, what would that scene look like? Now, again, with Roman, we don't have any direct image yet. Like we don't know how the sky would look. But what we know is like the different footprints, like the different regions of the skies that Roman is going to observe. So what people did is they simulated those images as well. So instead of using a directly observed image, they simulated the images, and these simulations are based on like previous observations, because like there have been other observations before which have observed like similar regions within the sky. So on the left, this is a simulated image from the Troxel et al. So it's called the Open Universe Project, and it's a great project where they provide you the simulated image for each of the detectors. Remember, Roman has 18 detectors. So it gives you a direct image for each of the detectors within Roman's footprint for the wide area survey region. And the third one for a grism simulation is something called a segmentation map. So segmentation map actually maps your direct image, like it maps that direct image to your detector. Like on the detector, where exactly are those objects going to land? That's what is called the segmentation map. So on the right, so this is a segmentation map where it actually extracts each of the sources from the direct image that you supply on the left, and then maps it onto the detector array, and like gives you like what the detector is actually seeing. So once you are armed with these three things, the ACD, the direct image, and segmentation map, then you can simulate your own grism scene. Okay, just quickly one thing. So on this image here, there are a large different types of sources. So there are bright stars that you can see here. There are different types of galaxies. There are ellipticals, there are like bulge galaxies, there are disk galaxies, there are different types of things within the image. But since I am focusing mostly on ETGs, so I wanted to extract sources which are designated as elliptical galaxies. So when I did that, this is what a grism scene looks like. So on the horizontal axis is the axis of dispersion. So that's where Roman would disperse the spectrum of the object, and on the y-axis it's the width of the object. So this is done using a software called Grizli. So if you provide Grizli with the ACD, with the direct image and segmentation map, you could create this specific grism scene using the Roman specification. So this is very important. Like when you are simulating this scene, you have to make sure that you take into account all the different things for the observatory. So, but one thing to notice here is like the flux within the dispersed image is really low. So the reason for that is I used a very like a not realistic ACD for the input simulation. So I used an ACD where the total mass formed was just one solar mass. It was kind of normalized to that. So I would need to correct that. It's a still work in progress. So once I correct for that, I am expecting there would be some like considerable number of counts within the dispersed scene. And here, what I did is I'm doing a very simple extraction. So what I mean by simple extraction is I just choose one of these galaxies, one of the bright ones, and then within that region, I'm seeing like what is the count, like how many like electrons are there within that specific region. So that's a very, very basic extraction process. And I'm just adding up the counts. And this is what the output looks like. So in blue here, it's the input spectrum at one solar mass. And in this violet or purple here, you see what we recover out from the simulation. So the few things to note here is that this is probably not very realistic yet because I'm playing around with the resolution of the extracted spectrum. So it's probably not at resolution what Roman would see. And I'm expecting when I correct for that, I should be able to see some of the very strong features that are still here. But you could see here that in the output spectrum, we are able to recover at least some of the features that Roman will observe. And some of those features, like it's not yet finalized what are those features going to be, but probably some strong features like the Balmer lines, the NAD, the calcium lines. If those features, we should be able to observe them using Roman Space Telescope. And we could use them further for different science cases. So for example, NAD could be used to trace the abundance of sodium within from the integrated light spectrum. And that's kind of so this is still a work in progress. So what is not done yet, one crucial thing that has not been done yet is like incorporating the real Roman noise when I'm simulating the grism scene. So like currently what the grism has, the simulation has is just the ACDs and the direct image. So the direct image only has the Poisson noise, but it does not have any kind of detector level noise that we expect to see. So once we incorporate that, so there is a simulation tool called Roman icing. So with that, we should be able to if we have a grism scene and if we provide that to Roman icing, then it should be able to incorporate all the different kinds of detector level noise into that scene and give you the output. And then you can use that do your extractions. Also, as I was mentioning, we need to do a better work with the extraction algorithm. This is currently very simplistic approach, but there are sophisticated programs which could do the extraction for you. We would need to look into those options as well. But overall, Roman Space Telescope, it will going to revolutionize the way we look at the cosmos. With its very large field of view, it has both photometric and spectroscopic abilities. And the most important thing is immediate public availability of the data. So if you want to do any kind of science with Roman data, you just have to create an account at Roman Research Nexus. You don't even have to have huge computing power at your disposal if you want to work with Roman data. And we are hoping that we should be able to do some kind of stellar population analysis using the grism data from Roman Space Telescope. And that's all I have for you all. Thank you so much for coming.
Any questions? Yeah, I'm probably really naive, but as far as the astrophysics is concerned, the fact that you really can get the same resolution on this much wider field than you have on Hubble. And so that must mean that, all access to everything, it must mean that the Hubble must have been completely limited by detectors and not by resolution, optical resolution. That's a fact.
So so the thing with Hubble is like so with Roman, we are just specifically focusing on the IR band. But the thing with the difference between Hubble and Roman is basically the field of view. Like Roman has the exact same angular resolution as Hubble, but the difference is the field of view. So the amount of data that Hubble would actually acquire probably it would take probably years to get the amount of data that Roman could get with just 1 point.
But I guess my question is just going off to get wide field of view isn't that's going to be degraded optically, and so it must not have been a limiting thing. Is this a huge advance in detector technology?
Yeah.
What this represents.
Probably. So if I'm not very wrong, so some of the detectors that Hubble uses, those are called like H2RG detectors, and these are the H4RG detectors. So these are like more advanced version of the detectors that Hubble currently have, and they are supposed to be like more advanced than what Hubble has. So Hubble is probably just limited by that capability, the imaging and spectroscopy capability. Yeah.
A little something to add is that you're basically at the diffraction limit for your mirror for both Hubble and Roman.
Yeah, that prompts my question. You've proven that for all this off-axis stuff.
Yeah, so clever design. Yeah.
Does it mean that Roman is going to have many more megapixels?
Yeah, so Roman, I think I have it somewhere.
So
300 megapixel, I believe. I don't know the number for Hubble off the top of my head, but for Roman, I think it was around 300 megapixels.
then if you compare
Yeah.
to the LSST talk that we had, I think they had like 64 gigapixels or something.
Yeah, right.
And that's just for one snapshot, one picture.
Yeah, let's just say like it's way higher. Yes.
Could you say something about the filtering and dispersive technologies that will be used in the
I don't think I know a lot about it. So what I know is like Roman has like 8 different imaging filters and 2 different spectroscopic filters. The prism is a slitless prism capability, but to be honest, I'm sorry, at this point in time, I don't know off the top of my head like what exactly is the technology behind those filters. Thank you.
So one question I have is, I understand that there are these multiple surveys that the telescope is focusing on. But what are the main science objectives?
Yeah.
Assuming that each of these surveys is trying to focus on something.
Right. That's a great question. Thank you for that. So, okay, let's go here like survey by survey. So the first survey, the wide area survey, it has both spectroscopic and photometric abilities. So it's going to give you like a very wide area picture in IR, within the IR band, what the universe looks like. And then when you move on to the time domain survey, for the high latitude time domain survey, it's mostly going to chart the cosmic expansion by detecting very far away supernovae. So that's why you have a cadence of around 5 to 10 days where you need to have the light curve for the supernova explosion. So with 5 and 10 days cadence, you should be able to get a large number of like detections for supernovae explosion. So I think here's a number count. So it's typically expected to get around 20,000 supernovae SNE count and at a redshift of around 2.5. So that's pretty far down the redshift as well. And for the last survey, the Galactic Bulge time domain survey, it's mostly focused on detecting exoplanets that we are probably not going to observe with direct transit methods, So we are going to rely on the weak lensing methods. So it has a very, very high cadence of around 12 minutes. So we are expected to find around 1,000 more exoplanets with the weak lensing technique and around 100,000 more with
Weak lensing is weak gravitational lensing.
weak gravitational lensing.
Okay.
Exactly.
So basically, IR stuff is more like cosmology oriented, and then this is more exoplanet oriented.
Yes, but this is still the filters that we are going to use. Those are still that have the band pass is still like IR.
Okay,
Yeah.
thank you.
Yes.
Thank you very much for the talk. I was just curious, I don't know if this is already decided or not, but say that you get those extra 5 years, will they be focused on looking better at these same fields, or are they going to be dedicated to explore a little?
Yeah, that's a great question. I don't think anything has yet been decided, but I'm pretty positive on this that they are probably going to open it up for new observations because they might be revisiting some of these footprints beyond 5 years, but because currently only 25% of the time is allocated for new observations. So if we go beyond 5 years, so there's a high chance that there would be scope for new observations. Yeah.
But two questions. One is, which orbit is this going to be in?
So,
Which orbit is the?
oh, it's going to be an L2.
Okay.
Yeah.
And then the other question is, now that you are working as a postdoc at Goddard, how does that differ from the academic environment here? How does the academic environment here prepare you for a position at Goddard?
Okay, that's a great question, Engels. Thank you so much for asking that. So, for the second part of your question, to be honest, the sole reason that I'm currently standing here giving this talk, I have got this position, is because how I got prepared within the department here. So, this department has for this fellowship, I had to write my own proposal. But this department actually guided me how to think out of the box and how to come up with your own proposal things, because you have to come up with something new that no one has thought about that before. So it has been really, really helpful with all the classes I did, with all the research work that I have been doing here, and I was fortunate to get a fantastic guy for my PhD advisor, Dr. Worthy. And so I would say whatever I'm doing right now it's a direct consequence of what I started doing here in WSU as a grad student. And then it's kind of a direct continuation of what I have been doing here. To be honest, I'm still working with Dr. Worthy in a couple of projects. So it has been a great experience migrating my PhD from here, because it provoked that it was very thought-provoking, you have to think about problems and how to solve those things. And all those helped me ultimately to write the proposal for this program. And that in turn got me involved with this fantastic project. So yeah, thank you so much for asking this.
I was supposed to announce, it fell down on my job. I'm supposed to announce and remind you there's a meet and greet for our prospective grad students from 3 to 5 in Q518. Q is Smith Center, uphillish, past shocks physics. So it's the Q building, 518, 3 to 5. Okay. Robin, I did it, wherever you are. And with that, maybe we should thank our speaker again.